Hello, today I'd like to talk about acid-base reactions, also known as neutralization reactions. We're going to deal with acids and bases, and acids are of a certain nature with a certain reactive ion, at least one definition says so, and bases are of another type of reactive nature. It's not that they're opposites, but they rather combine to neutralize each other, and when acids and bases combine, you'll end up with salt and water. Okay, so some type of salt and water. So let's practice a couple reactions where we're going to predict the product. So we should get some type of salt and, of course, H2O at the end. Okay, so here we go. We got magnesium hydroxide. When you write that correctly, it looks like this. And there's hydrochloric acid. So actually, this is the base and this is the acid. Notice I'm underlining certain ions, which I'll get to shortly. That's MgOH2. Sorry about that. And when these combine, let's go with it's a double replacement reaction or double displacement reaction, depending on how you learn that. So this is going to be your salt, okay, MgCl2, and this is going to be highly aqueous. In other words, highly soluble. In other words, no precipitate. And then, of course, water. Now, it's the water. That's an L, by the way, for liquid. The water here, this is important. Let's talk about this real quick. The water doesn't show up. I'm sorry, let me say it this way. When you do this reaction, you don't see anything happen really. But something happened because you produce liquid water. Okay, water is a product. And even though it's not considered a solid precipitate, it is something that is non-aqueous, something that was produced. But since these things, since this is dissolved in water and this is dissolved in water, in other words, I have aqueous solutions, it's very difficult to tell that a reaction actually occurred when you talk about magnesium hydroxide plus hydrochloric acid or a acid-base neutralization reaction. But you do. So you would not necessarily write NR for no reaction, you would write like no apparent reaction. Okay? So let's try a different one. Acetic acid, we'll write it inorganically. HC2H3O2, that's aqueous, plus barium hydroxide, also aqueous. And of course, we'll get a salt, and the salt this time is barium acetate, BaC2H3O2. I'm kind of squeezing it in here, I apologize. Plus water. There is your compound that is produced, okay? So again, you can go through and we don't have to do a third one. But anyway, those are writing neutralization reactions, okay? You should get salt and water most of the time, okay? So a couple notes on what acids and bases actually are, at least what's called the Arrhenius definition. And the Arrhenius definition says that the H plus ion is the essence of the acid. So if you look at monoprotic acids, diprotic acids, triprotic acids, I think you can probably apply this to this to this and figure out what those mean. What we're looking at here is H plus. That's the commonality, okay, between all these acids. So, and that's really a single bare proton. And really what happens here is this. If you have the hydrogen ion, okay, the hydrogen atom, and you have a single proton in the middle, and then you have an electron floating around the outside, and I'll make that blue, okay, that's hydrogen. You have one proton, one electron, okay. The charge in the hydrogen atom is 0, okay, because you have one proton, or at least they balance. You have one of each, proton and electron. If you make the hydrogen ion, you lose that proton. You lose that electron. All you have left is this positive proton in the middle. So the H plus ion is simply just a bare proton. Very, very reactive species. Okay? So that's why they call it protic. Monoprotic, single proton, single H, diprotic, double proton, double H's, etc., etc. Now, the one thing I want you to be careful on is when we talk about bases, bases have what are called the hydroxide. But now, so that's the essence of an Arrhenius base. But just be careful with alcohols, because alcohol looks like this. This is something called methanol or methyl alcohol, and this is ethanol or ethyl alcohol. Notice you see this OH here. That is something called a hydroxyl group, not hydroxide, and it's sometimes mistaken as a base. It's not. It's actually an alcohol. Okay, so just be careful with that. So when we talk about some of these things, we can actually do reactions with this to predict how much of a certain substance we might need. So this one says, what volume of a zero point 0.1 molar HCl solution is needed to neutralize 25 milliliters of a 0.350 molar NaOH? Now, you can use MAVA versus MBVB. This looks like the dilution equation, doesn't it? Okay, so this actually works, but it actually is most effective and most easily used when you have a single proton or monoprotic and a single hydroxide ion. If you have a diprotic or two hydroxides, you got to do a little magic here mathematically, but it still works, but it's easier to do it a different way. So with the stipulation that you have a single H and a single OH in your reactants, or as your reactants, you can use the MAVA. So what you would do is this. This is the molarity of the acid, volume of the acid, molarity of the base, volume of the base. So the molarity of the acid says what volume. So I know that I have a 0.100 molar HCl solution. It says what volume, so I'm going to go VA. That's my X. Okay. And then it says you have neutralized 25 milliliters of this. So it says what volume. Let me see here as our question. So we have MB, that's 0.350 molar. And we have 25 milliliters. I'm going to keep it in milliliters. Therefore, my answer will mathematically come out in milliliters. Now, that's a little confusing because molarity is really moles per liter. But the cool thing about this is these are going to cancel, so it really doesn't matter, okay? So once I get everything to work out, I'm going to multiply the right side together. So this is 0.35 times 25. That's 8.75. And I'm going to divide out the 0.1. And we end up with, oh, whoopsie. And we end up with 87.5 milliliters. Of what? 87.5 milliliters of the HCl that you need to neutralize this stuff completely. So they'll neutralize or perhaps cancel each other out. Okay? So that's one way that we can calculate with this. Here's another one. How many grams of calcium hydroxide are needed to neutralize 25 milliliters of 0.1 molar HNO3? So you're thinking, oh, wow, MAVA, right? MBVB, just like we used. Careful, calcium hydroxide has two hydroxides in it. Okay? So we can solve this a different way. It's a little longer, but we can still do it. So we have HNO3. Let's write the reaction. It gives us calcium nitrate and water. Now we got to balance this because we're going to use some stoich here, okay? So this is also solution stoichiometry applied to acids and base reactions. It's all the same. This could be a limiting reactant problem, okay? So we've seen that before too. Not quite, but we can move on. We'll move on to that later. So what do we need? 2 here, and I think that does it, okay? Let's see, 1 calcium, 2 nitrates. Yeah, I think we're okay. No, we need a 2 in front here. Okay, that should do it, okay? So what I want to do is, and the way I always advise my students is take the stuff you know most about. We know most information about the HNO3. Start there. So what I'm going to do, what am I going to do? I'm going to solve for moles, okay? So I have molarity, and molarity is moles per liter. So moles is equal to molarity times liters. And once I can get to moles, I can apply stoich. And once I get stoich done and set up a mole ratio through stoich, I can solve for the other substance, whatever they're asking for, okay? So here we go. Molarity of the, this is the acid. So let's go here. That's 0.100 moles per liter. I got that. That's this right here. Times, now I got to convert to liters. Okay, because I'm using the value of liters. So I end up with 0.00250 moles of HNO3. Okay, so that's all fine and good. That's how many moles of acid I have. The question is how many moles of base do I need to make this thing work or to completely neutralize? Is that because that's what the question says. So what I'm going to do next is take my 0.00250 0.250 moles of HNO3, and I'm going to convert that to the base using a mole ratio. Okay, so here's my mole ratio. It says, let's look at the question, how many grams of calcium hydroxide? So I got to get to calcium hydroxide. I'm not in calcium hydroxide, I'm in HNO3. So let's use a mole ratio to get to that. So this says I'm going to have 2 moles of HNO3 to convert to 1 mole of calcium hydroxide. So we need to divide this by 2. And that should give us 0.00125. Okay? Moles, but not HNO3 anymore, calcium hydroxide. Okay? Now, let's go back to our question. We got moles of calcium hydroxide. Always keep aligning yourself to the question. What are they asking you for? How many grams of calcium hydroxide are needed? Well, this is how many moles. Well, this is easy now. Once I have moles, let's just convert to molar mass. Using molar mass, let's convert to mass. Okay? So calcium, I believe, is 40.1. So take that, put that in your calculator. Plus, let's see, we have 2 oxygens. We'll call that 16 times 2. That's 32. Plus 2 hydrogens. That gives me a molar mass of 74.1. Okay? So molar mass is 74.1 grams of calcium hydroxide. Gives us, times 0.00125, gives us 0.0926. So our final answer, oopsie, 0.0926 grams of calcium hydroxide. Okay? So that's a couple problems there. So what we'll do is we'll move on to a different problem in the next video. Okay? So if you have questions, let me know. But that's it for now.